yeah, you can see this line here to divide into between quantum and a classic description, where we have force fields, of course, point charges at locations of the atoms, and which can be coarse grained, for example. And I had another line here because, oops, this is where we're standing. I do a continuum approximations such that the models are based on partial differential equations, which is an area where I feel sort of comfortable, and which is something that is useful in itself, but also in sort of mixed up with other models to do some neat multi-scale models. So in itself, this is probably some things you know, but in itself it's useful because you can compute mean field potentials, mean field forces, and also sort of equilibrium calculations, for example, free energies. But you can mix them up with quantum calculations and straight molecular dynamics and QMMM and PBSA, for example. So so what we're looking at here is the Poisson-Boltzmann equation, of course, that starts from just doing classic electrostatics on a continuum medium where the point charges that are the ions that can move around, and if you use this Boltzmann statistics, you get this equation here, which is nonlinear, and then if you linearize for low low charges, you can linearize version. We're going to focus on the linearized version for this for most of the presentation. Towards the end, I'll come back to the previous one, which actually aligns a little bit with what Antonio was presenting yesterday. So how does this boil down in the context of the molecular simulation that we want to do? Essentially, well, we have the structure from a protein data bank, apply a force field, we have the radius of each atom, we roll a probe over the totality of water molecule around it, and we generate what we call the different variations of the surfaces. We usually use the red one here, the solid extruded surface. And so we have two regions: an internal region where we have a low dielectric constant, the point charges, so a classic Poisson equation of electrostatics. And then you have the interface, and outside the Poisson-Boltzmann equation. And this boils down to this system of PDEs down here. So the Poisson equation on the top, Poisson-Boltzmann on the bottom, interface conditions at the molecular surface. So this is, of course, not new, and here this is a very small subset of the amount of the number of software that out there that can solve this, and a few of the developers of these software are present in the room. But I guess and you can find codes from finite difference to finite elements to boundary elements and whatnot. So, but perhaps the most used ones are by far APBS and Delphi, both APBS mostly in the finite difference version. They work really well, but of course, finite difference has its difficulties when you have a sort of a staircase kind of representation of the dielectric constant. It's difficult because you need to somehow modify there. You have to transfer charges to a mesh. That's difficult, and also the boundary conditions at infinity that should mimic the fact that they're going to zero. Now there is software in particular, for example, LibraryMPP PB, who solves a few of those things in particular by using the regularized version, and no need to transfer charges to a mesh, and they do sort of fancy stuff to get better accuracy on the interface, and no need to have this staircase representation. So, but we chose the boundary element method, basically because, to our eyes, I guess, the most of the interesting stuff is happening at the interface, and this method actually focuses at the interface. And we like the property that by construction the potential goes to zero and infinity, so we don't need to have any boundary conditions there. In the boundary element method, rather than having a system of partial differential equations, we have a system of integral equations. So these two, the top one is the equation for the Poisson equation inside. The bottom one is a Poisson-Boltzmann equation outside. So this is one of the forms of the boundary element method for this application, the simplest one, actually. And we have a recent publication where we compare a few of those. In fact, you can have an infinite number of formulations. And this is the simplest one. It's not the best in terms of how it behaves, but it's somewhat useful. But in the context of what I want to show, it's enough. So this generates a system, a linear system of equations here, where these 2 by 2 this 2 by 2 block matrix represents these integral operators, and you solve for the potential and its derivative on the interface. And that you use to, for example, compute, if you want to compute free energies, that result of the linear system you would plug into the integral equation down here to get the reaction potential, and that reaction potential you use to compute the polar component of the solvation free energy. So this is, I mean, the problem with this is that it's hard, okay, and for many reasons. For starters, meshes are hard, and I need to thank Walter here. I thanked him last night actually about this. We use NanoShaper extensively, which generates very nice meshes for us, even though it wasn't originally built for numerical calculations on the mesh. The triangles are actually very nice compared to other software there is out there. And the code is hard. You have difficult integration schemes, and not in the formulation that I showed you before, but in general, you might get hypersingular integrals, which are hard. The matrices that you generate are dense, so every element of the matrix is important, and to accelerate that, you need some sophisticated acceleration algorithms, such as the fast multiple method, tree code, pre-corrected FFT, and whatnot. But what was more important to me actually is the fact that prototyping and maintenance is hard, okay? And I know this because I actually, during my PhD, I did do my own version of a code, okay? 2.5 years of my life that will never come back, and quite a few thousand lines of code, and I developed PBNJ. I'm really proud of it, and we continue using it. Which it's a code that runs in Python, uses GPUs, and it's accelerated with a tree code based on Robert's work. So it's relatively fast, and it has a low memory footprint, so it's good. But the problem is that if I want to continue working on this, it's either me doing the work, or I had a couple of students that sat down for 1.5 years, they learned the code, and then they were able to contribute to it. So unfair for them, slow for me. And not the best way to push a research program, right? So that's why I started looking for alternatives, and I found this library, MPP, which is developed by our good friend Timo Becky at UCL and the math department there. It's a boundary element library, as it says. It's mostly Python. It has high-level abstractions of the integral operators, but under the hood, it's actually very efficient. Okay. And it's built by people that are very careful about their work. So this is a story I sort of like to tell. That when I was back in Chile, starting my faculty position in Chile, the undergrads need to do a undergrad thesis. So an undergrad knocks on my door, asking, "Hey, do you have a project for my undergrad thesis?" I was actually reading up on this right at that moment, and I told him, "Well, why don't you learn to use this library and try to reproduce the results that I got with my code?" Which, when he left, I realized it was a horrible idea, considering it took me 2.5 years and I was sending an undergrad to do it, right? So I thought that, well, maybe I was going to get fired, or at least the guy was never going to come back. It turns out that 1.5 months later, he arrives with results, okay? So after I got over the frustration that meant that an undergrad did my work in 1.5 months, and of course, I never told the funding agencies, but probably they wouldn't be very happy. But it turns out that it's just the library is very nicely built, right? And with, say, 20 lines of code, you're good. So, and it's also very intuitive. So you can see how here we're generating the same matrix that I was showing before. So 0.5, identity, double layer, single layer. So the same thing that we were showing before. And boom, you have a result. This actually made me realize that this was sort of an opportunity. Now I can have students that with a few months of training, they can actually be doing science and not worrying about the software development. So one minor difficulty, of course, is that, I mean, you can't just put this out there for the community, because you still need some knowledge of the mathematics behind it. So you need to know about function spaces, about potential layer operators, about preconditioners, and all this. So that's why with a group of students here, we figured, hey, why don't we do just a wrap around this, and with a one-liner on a Jupyter notebook, you can do your calculations. And that's how PBNJ was born. Not peanut butter and jelly. It's Poisson, Boltzmann, and Jupiter. That sort of goes in that direction. And one thing that we thought about at that point is let's think about a structure of the code that would make sense and that would make sort of physically inspired. And that's how we came with a structure where you have a simulation class that stores everything, but essentially the meat, the core of the code is this solute class, where you store all the physics, all the physical parameters, the dielectric constants, the charges, the surfaces, and then once you have that, you just one line of code, and you can calculate your potential, calculate your salvation energy. And so this is just an example on how it looks. You import the library, you generate a simulation, you import a structure to get a solute, and then just you add it to the simulation, and then one line of code, and it generates all these intermediate with all the intermediate results, which is a cool thing. And you can query, okay, and you can query. So and if later you, for example, you want to calculate forces, it will reuse everything that is before that has already been calculated. And again, it's more of an interactive sort of scheme here, and as you move forward, and you can go all the way and even plot and have a lot of control over the plotting. So that's sort of cool. And for us, not only the fact that it's easy to use, but the way we built it is sort of a playground to us. With the years, we've sort of started getting more into the model development side of things, and we build it such that it's a linear system. If you have a left-hand side, you have a right-hand side. You change your model, but if you have a left-hand side and a right-hand side of a linear system, you're good, and this will take care of everything. So also, I believe this is one thing that I truly admire of the whole computational chemistry community, is that it's a community that is very, very much worried about the quality of the software that they're using to do their science. Okay, and these are two community-wide efforts that I really like, mostly in the US, BioExcel in Europe, that promote good software practices, promote easy-to-use software, interoperability, and sort of setting standards on how software should be developed in these applications. And honestly, in the PB side, we were sort of lagging here, and I was hoping this effort would align with these community-wide efforts. So that said, we are actually tackling quite a few applications and quite a few problems in my group using this technology. And today I want to talk about just a couple of them, but we're looking at a lot of things, say from biosensors to some virus relevant simulations on the application side. We have problems in the algorithm side, say faster algorithms and parallel computing. We're looking also more in the mathematics side, so that's measure refinement. So we have problems from everywhere, so we're trying to do them all, hopefully. So the first one I want to talk about is accurate force calculations. This is work from a very talented, actually undergrad with 2 papers. It was just amazing, Ian. And this is work that we did with Horacio, one of the authors of this presentation, and we worked very extensively on this. So the force calculation with PB is a hard thing to do. The main problem, especially considering if you use finite differences, is that you need the electric field on the interface, and that's a hard thing to have. Okay, so usually, and for example, in APBS, you use a modified representation, so such that you can actually do those derivatives on the interface. So what we did here is we compared a few ways to compute the force and saw some benefits of using this sort of algorithm, meaning the boundary element method. So the sort of the simplest one, I guess, is just, okay, let's compute the energy in 2 different positions, and that difference will give us the force. Now, of course, that's hard, because if you want accuracy, this h needs to be small, but if h is small, the g is going to be very similar, so you need a very accurate calculation of your salvation energy to get this. So that's hard, but it's still a good sort of it's good to, it will it will give you at least the right sign. It will give you the right trends. So it's good to have it there. Then there are two ways to compute the force more directly. One is taking the derivative of this energy functional. This is work by Gilson in the 90s, which is very nice because once you take that derivative, you can actually separate the force in three terms that are have a lot of physical meaning. So this would be the force on the charges. The second one would be the force due to the dielectric interface. The third one would be the force due to the salt in the jump in the salt concentration. So it's essentially the osmotic pressure. On the other hand, we can compute it with the Maxwell stress tensor directly. But as you can see in these two cases, the most problematic thing is that you need to compute the electric field, especially on the interface. That's hard. So you need the force in two parts, right? First here on the charge itself, which we compute as it is on the we're looking at the electric field of the reaction potential. Actually, the derivatives are not that terrible, so we can get away by computing the potential in nearby places, and we just go with a finite difference kind of approximation. On the interface, though, the good thing is that we were using, by luck, piecewise linear boundary element method. What it means is that we're assuming that the potential and its derivative vary linearly in each one of these panels that are on the surface. And the good thing is that we're tracking then the potential on these vertices. And if we have the potential on the vertices, we have the electric field directly. I mean, if we're assuming in the context of a piecewise linear approximation, this is exact, essentially. And so we tested this. The first test we did was on the single lysozyme. So if the molecule is by itself, the total force should be 0. And here we compared our boundary element approach with the two methods, the energy functional method and the Maxwell tensor method. And as you can see, as you refine the mesh, actually the force does go to 0 as expected. And here we try to find a difference using APBS, and as we refine the mesh, also it starts a little bit higher, but it does go down, and then eventually, I mean, my computer crashed by then, but it should go to 0 eventually. Now, one thing to note here is that, let's say, what is a reasonable mesh, right? And for example, for a energy calculation, there's evidence that in finite difference, you at least should have a mesh of 0.5 angstroms or less. And so mesh of 0.5 angstroms here would be this one. The force is still very far away from 0. As you refine, it goes down, yes, but it does seem that if you want to compute forces, you need to really ramp up your accuracy. On the other hand, with boundary element methods, in our experience with a mesh of 2 vertices per square angstroms, 4 vertices per square angstroms, we should be good. And with 204, we already, for example, for the Maxwell tensor, we're already pretty close to 0, which is it's remarkable in the sense that we're seeing that even though we're computing the derivative of a value, the mesh that we need is it's the same mesh that we are using for energy. So that's a good thing. So then we started, well, the idea of forces is to compute interactions, right? So we looked at the classic Barney sparse star complex. So we started pulling it away, and here we're looking. So I'm using a different naming here, but method 1 would be the numerical derivative, and method 2 is the energy functional. So and method 2 and method 4 are right one on top of the other. Don't mind about the green line really. And we can see actually things that have been seen before. For example, there's evidence from the group of Emil Alexov that shows this sort of behavior. They call it soft landing. That when the interaction sort of grows, the force is bigger, but there's a point where they want to repel slightly. And we're looking at other cool applications. So this is cool work that started with a collaboration with Horacio, one of the authors here, who was talking to people in Spain that are poking Zika virus with an AFM tip. And they were sort of puzzled because, well, the Zika virus has this icosahedral symmetry. So you have the red pole here is what they call the threefold symmetry, twofold symmetry on the blue one, fivefold symmetry on the red one. And they were puzzled because they were poking this, and they saw that the effect as they approached was different depending on the orientation. And according to them, the electrostatic effect was a global effect. So they didn't understand why this would happen. So we said, okay, let's try and model that. We essentially have this. This is the Zika capsid, and we approached a tip, like modeled as a surface as a charged surface, and we approached it and looked at what happened. So we actually wanted to see the effect on the charges themselves. So here we used the method that separated them into three terms. So these are three terms. The blue one is the force on the charges. The orange one here, the force on the dielectric interface. The green one due to the salt. The red one is the total force, and this purple line here is a fit of an experimental fit, essentially. And we were going to be happy if we were in the order of magnitude. We were never hoping to be this close. So actually, it was surprised and sort of said, okay, we're not that bad then. And considering that, we started looking a little bit deeper. And the question was, is this a global effect or a local effect? So this result here on the right, we're showing essentially when the tip approaches, what atoms are feeling more force. And the ones that are here in blue are the atoms that are feeling more than 1% of the total force. And you can see how it's a very local effect. So this sort of went against what they thought was the case, that the effect was more global, but it actually made sense in the point of view that, hey, so if it's local, then the orientation, if you're poking the threefold, the twofold, or the fivefold, you'll get different answers, different behaviors. So that was cool. That was published recently. This is 2022 and 2023 on these two works. How much longer do I have? 5 minutes? Really? Wow. Okay, I thought I was okay. I'll do it in 5 minutes. So then this is what I wanted to say a little bit on work in progress. I'll keep it in 5. So one of the limitations of this boundary element method was a linear thing, right? Yesterday was a discussion, and I said it in the beginning. The boundary element method is limited there. Also, is limited to piecewise constant variations of the field variable, so the dielectric constant cannot be variable. So that's why we started getting into how can we add more flexibility to the method, and here what we're going to do is do a coupling of finite elements and boundary elements. Okay, so this is a very much a proof of concept work that we're doing in collaboration with the MPP team at UCL and Nika Bossi in Kingston and also in London. That and as a proof of concept, we said, okay, let's mesh the molecule with finite elements and use boundary elements elsewhere, so that the potential does go to 0, and inside the molecule we can do whatever we want. Okay, so the matrix now changes a little bit. Of course, the top here are finite element matrices, the bottom here are boundary element matrices. The problem is that you need something to be able to read these and understand what to do. Luckily, these guys did it for us. So BMPP and Phoenix X, which is one of the big finite element libraries, do interact. And so similarly to the previous case, the generating the matrix is super easy. This is of course the code is much longer, and I can show it later. But the meat is here, right? This is where you have the matrix B00, B01 would be the top 2 blocks, and B10, B11 would be the bottom 2. So you can see how A here is a Phoenix operator, is a finite element matrix, and this DLP and SLP here are boundary element matrices. So we can do that. So in this case, the coupling, we made it with the simplest case possible, which is the Johnson-Nedelec coupling. And so once we had this, we say, okay, what can we do? We did some validation, of course, but what can we do? I remember this nice work from the group of Milalek stuff. Of course, this is older ideas of having a Gaussian permittivity that varies in space, and so that's something that we couldn't do with BEM, and we can do now with FEM. and this is we're getting the same results as APBS, for example. We used APBS even though that Delphi has this implemented. Getting the electric map from Delphi was impossible, really. I mean, maybe it's possible. I looked enough at it, and APBS was easier to control. We can go later and talk about that. So, but we're getting the same result. We're getting a 0.5 difference on 0.5 kcal difference, which, considering that in the end it's a different model because the boundary conditions and infinity are different. So it's normal to get a slight difference. So, but I'll be honest. So we tried on a different on bigger cases, and the problem is that the time to solution is getting longer and longer, and it's a lot of motivation to start working on better formulations and better preconditioners, and we're pushing hard on that side. But I'll be honest, the reason why I wanted this, and I disclosed this to the team, to the BMPP team later, actually, I wanted to have nonlinear PB, okay? And this is work by Camila and Byron, 2 students at home, and this is something we've been doing heavily with Marcia. These are essentially the difference between linear and nonlinear. For example, for ubiquitin, which is not too bad, the bars there are in KT over E. But if you look at something like a nucleic acid, like a DNA, the difference is much bigger. And so the good thing about finite elements is we can do nonlinear, but first we need to know where to mesh. So the question that we had, and this is where we're standing, I don't have a result yet, but this is where we're standing. We're looking at this and we're saying, okay, can we predict the regions where nonlinearities are important, such that we can mesh it with finite elements? And then we have a small nonlinear finite element, and the rest will be everything with boundary elements, making it nice and efficient. And these are different cuts of this molecule on the right. And apparently we do have something. Okay, when we looked at this, the first thing was like, hey, it seems like regions with higher are going to be sort of surrounded by the molecule. Sorry, I didn't mention that the green line, the green dots here are the surface of the molecule. So we said, okay, maybe we sort of defined a coverage level, and we wanted to see how that correlated with the error, and we didn't see much of a correlation, and plus it was hard to compute. So we said, okay, let's focus on easier things to compute, and that's why these results show the correlation between for example, the Coulomb potential at each point with the error, the total linear potentials with the error and whatnot. So the total linear potential does seem to have quite a correlation. So, for example, maybe we'll have to do a linear calculation and get these results. Look where the errors with these results, predict where the errors are high, and then do a second calculation with nonlinear, or maybe even with the Coulomb potential, it will be enough. So this is where we're standing. So apparently we can predict that, and we're heavily working on getting those nonlinear regions in. So with that, I finished, and I think I kept my promise of 5 minutes, but just some conclusions. BEM can be fast, accurate, and flexible, and easy to use. So what we've done is one-liner to this application, and we're getting the FemBEM support in the code. It's underway, and apparently we can predict the regions of nonlinearity. So that's what we're pushing at this point. So thank you.
Thank you. Any question from the audience? Thank you. So you showed these integral equations at the beginning with the ionic strength. I actually didn't recognize the equations. I mean, are those consistent with the ones developed by Ufer and Berenson in the 90s, or is that because I was a bit surprised to see that the ionic strength separated out, and only showed up in one equation,
let me
for
see
example.
If this is
you mean some
these equations, right? So the separated out mainly. So they're coupled on the interface, right? So this is the ionic strength, right? So but the top equation is essentially the equation just inside the molecule where there's no salt.
So are you aware of the integral equations developed 30 years ago by Berenson and Ufer?
I don't remember the Berenson ones, but That's a two for, okay.
Yeah.
Then yes, of course. Thank you. I had the first name of the author, but so that formulation is actually more used in this context, and because it behaves better in terms of the number of iterations. So essentially, the condition number is a lot better. So these are consistent. Yeah, they give the same result. Yes. Thanks, Robert.
I actually have a question
Yes.
too. When you calculate the forces, you mean you treat your object as a rigid body and you calculate the overall forces, not the forces on each atom.
And
in that case, you might have problems with the definition of the molecular surface.
I'm not sure I understand the point, but yeah, we're defining as a yes, I see. I guess I see your point. We are defining it as a rigid body, but one of the formulations does sort of separate them in this sort of more physical, intuitive way.
Mhm.
But that wouldn't know, if you want to know the total force on the atom, you would need to add the effect of the. So you would need to do some sort of interpolation of these two terms to the atoms.
Yes.
Yes. Yes.
Thank you. That was extremely very interesting. So the nonlinear will be wrong pretty much where you have where PNP crashes, where charge exactly. I mean, it's nonlinearity
Yeah.
going off. So the charge close to the dielectric boundary. That's it, pretty much. It's very local.
No, yeah. Well.
So you can just set up
So
geometry
actually, yes.
criteria.
So what that was we want to be we want to avoid meshing as much as possible. So,
Right, but basically everywhere you have a fixed charge
So, yeah,
inside the boundary and boundary is
we might-
closed, it will be
might end
wrong,
up with
that's
just
it.
a layer,
Yeah.
right, around it.
No, it doesn't have to be around the whole surface. Only where the charged particles are actually close.
Okay, fair enough.
Basically, run PNP, see where it crashes. That's your
Okay,
condition.
got it. Thanks.
Okay. Then thanks again, the second speaker of the day. Thank you.